All right, guys, so we're going to continue along with some of our ideas for introduction to calculus today. We're going to continue to talk about limits, and today, instead of talking about limits from a graphical or a table perspective, we're actually going to look at them just strictly algebraically. So the way that we're going to do that is we're going to work on something called substitution with limits. Okay, so let me go back to an idea that I mentioned the other day. Let's say, for example, you were going to find what's the limit as x approaches 2 of the function, I don't know, let's just say x plus 3. Okay, well, if you were going to x plus 3, this is a linear function, and it has a y-intercept of 3, so 1, 2, 3. And then the slope of this function is 1, okay? So if we were going to do some different things with this, we go up 1 over 1, up 1 over 1, up 1 over 1, down 1 to the left 1, down 1 to the left 1, and so on and so forth, and we would have a line that looks like this, okay? And if we wanted to look at this from a purely graphical perspective, we talked about for a limit, you need to look at what's happening to the left and to the right, and as long as we see the same thing happening on both sides, then the limit exists. And in this case, as we are approaching 2, or an x value of 2, what we see is the y value approaches 5 from the left, and it approaches 5 from the right. Therefore, this limit is 5. Okay, but an easier way to do that, and this is what I mentioned the other day, is that if I can just go ahead and plug 2 in right here, we'll do it. And if I plug in 2, I get 2 plus 3 equals 5. Okay, so an easier way of doing this instead of looking at it as a graph is simply to just do it algebraically and directly substitute in 2 for x, and we get a limit of 5. Okay, so like if we're talking about like evaluating limits, evaluating by, I don't know, I don't want to say graphing or table, we'll just say like arithmetic. Okay, well, one thing you could do is you could use direct substitution. If you can simply just plug in the value that you're supposed to be approaching like we did on the last problem, go ahead and do it. I promise that'll be the easiest way to evaluate the limit. Okay, now let's think of an idea where maybe, or a situation where maybe this fails. Let's say that we were going to look at this function, f of x equals x squared minus 2x minus 3 divided by x plus 1. And let's say that I wanted to know what's the limit as x approaches, we'll start out with this. Let's say we wanted to know what's the limit as x approaches 4. Okay, well, let's check if direct substitution works. Okay, now there's only a couple of different things that are really gonna make direct substitution not work. And for us, we're really only gonna see one scenario. And the biggest scenario that I've mentioned over and over the course of the year is that we are not allowed to divide by 0. As long as I don't divide by 0, then direct substitution should work. And in this case, 4 plus 1 is 5. That's fine. I'm gonna have a 5 on the bottom, and up on the top, 4 squared is 16. 2 times 4 is 8. Minus 3, 16 minus 8 is 8, minus 3 is 5. So what I can see here is in this function, as x approaches 4, my y value approaches 1. Okay, direct substitution worked here, so let's go ahead and use it. We did, and we got our answer. Okay, now, what if the next thing I ask you is what's the limit as x approaches negative 1? Okay, let's try direct sub. Okay, if I try direct substitution on this, negative 1 squared is 1. Negative 2 times negative 1 is positive 2 minus 3. Okay, and then on the bottom, negative 1 plus 1 is 0. Okay, well, 3 minus 3 is 0. Divided by 0. I can't divide by 0. Therefore, in this particular case, direct substitution does not work. Okay, so if I'm going by arithmetic here, if direct substitution doesn't work, we must have another way to evaluate this, or the limit won't exist. So our second strategy here for evaluating through arithmetic is to try to factor. Okay, Let's see if factoring works, all right? If you remember from pre-algebra and algebra 1, the top of this is a quadratic. You can use the shortcut here because the leading coefficient is 1. I'm looking for two factors of -3 that add up to -2. They would be x minus 3 and x plus 1. And why did factoring help us? Well, in this case, factoring helps us because when we factor this, we are now able to remove an x plus 1 from the top and the bottom. So now what we're doing, instead of evaluating this entire thing, is we're just evaluating the limit as x approaches -1 of x minus 3. And this direct substitution does work with, I can plug in -1 directly. -1 minus 3 gives me a value of -4. Okay, so for this function, the limit as x approaches -1 is -4. All right, so we're going to add this to our list here. Direct substitution doesn't work. We can instead, if we would like, try factoring. Okay. Let's go ahead and let's see if maybe this is simply to help us review factoring here. Let's try an example. Okay. So here's my function. It's going to be a big function. We've got 4x cubed minus 12x squared minus 9x plus 27, all divided by x squared minus 9. Okay. And what I'd like us to try here is what's the limit as x approaches 3 of this function. Okay, well notice that when we do this, I don't really care about what's happening on the top. But if I try direct substitution on the bottom, 3 squared is 9, 9 minus 9 is 0. I can't divide blah by 0. So instead, let's try factoring. Okay, so instead, let's factor. All right. Now, I'm not saying that factoring is always going to work, but it might. So if it does, let's go ahead and use it. So let's start out just with what we know to be the easiest thing here. Let's look at the bottom. X squared minus 9 is the same thing as x plus 3 times x minus 3. Okay, that's a difference of perfect squares. It can be factored as a plus b times a minus b. So in this case, our a is x and our b is 3. All right, so what we're looking for here with factoring is maybe we can divide, since we're finding the limit as x approaches 3, the thing that would cause the bottom to be 0 is if I plugged in 3 in this set of parentheses. So what our hope is by factoring the top, we will be able to remove this x minus 3 from the bottom. Okay, so let's start out on the top here. Let's look, and what I see here is I see 4 terms, okay? And from algebra 2, you'll remember when you have 4 terms, you should try to factor by grouping. So looking at those first 2 terms, I can take out a 4x squared, okay? And I would be left with an x minus 3, which is good because I see an x minus 3 on the bottom, but I can't cancel this out quite yet. I'm going to go ahead and write down that minus sign, and next up I see a 9 and a 27. Okay, so I'm going to take out a 9, but really I took out a -9, which means these signs need to flip, so this is going to also be an x minus 3. Okay, this is good because now we have the same, and again, I should have mentioned this, but you should be writing this part every time as part of your work. Okay, just proper notation means every step of the way we write down that limit as x approaches 3. Okay, now I've got the same term in both sets of parentheses here, so I can go ahead and factor out that x minus 3 on top. I'm left with a 4x squared minus 9 on the outside, okay, and I've got this x plus 3 times x minus 3 on the bottom, and as we mentioned, this is what we were trying to remove. We can now do it, and that leaves me with this. The limit as x approaches 3 of 4x squared minus 9 divided by x plus 3. Now, you could factor the top of that a little bit more if you want. There's no need to, though, because at this point, by plugging in 3, I no longer divide by 0. So whether or not the top is factored, I can go ahead and try direct substitution here. 3 squared is 9. 4 times 9 is 36. This is the only step where you don't need to write that limit part. Once you actually start directly substituting, it is not necessary anymore for me to write this down. So we'll have 36 minus 9. And then on the bottom, 3 plus 3 is 6. So I have 27 over 6. Both of these are divisible by 3, so 27 divided by 3 is 9. and 6 divided by 3 is 2. So my final answer here, the limit as x approaches 3 of this giant function is 9/2. Okay, so once again, the strategy of direct substitution did not work, but when we tried factoring, it did work. It allowed me to remove the factor in the denominator that was making me divide by 0, and it allowed me to evaluate my limit with direct substitution. Okay, so it's not so much that direct substitution doesn't work, it's just that it doesn't work at the beginning, so we need to do a little bit more work before we can get to that point. Okay, all right, a couple other examples here. Let's go ahead and let's see if we can come up with one here. So let's go the limit as x approaches 5 of, let's try the square root of 2x minus 1 minus 3 divided by x minus 5. Okay. Now, once again, direct sub, we should try it. Okay, but right here, if we notice that if we plug in 5, 5 minus 5 is 0. So direct sub doesn't work. Okay, direct sub does not work. So we need another strategy. Okay, now this is a little bit different from the last problem because in the last problem we had polynomials on top and bottom. Okay, things that had exponents that were easy to factor. This, on the other hand, has a square root. Okay, so this is going to be a new strategy that you maybe have seen something that's actually similar to this in trigonometry, but maybe haven't seen a whole lot of it in algebra. So I'm going to go back real quick to an idea of, I actually just mentioned it on the last problem, although I didn't mention it by name. There's something called a conjugate. Okay, and the thing that's special about a conjugate, so let's say, for example, we had x plus y. Okay, the conjugate of x plus y is x minus y. Right, and what you'll see here is when you multiply two conjugates together, it becomes x squared minus xy plus xy minus y squared. Okay, and what you'll see is that anytime you multiply two conjugates together, what happens is the middle cancels out, and I'm just left with a difference of perfect squares, x squared minus y squared. That's why whenever you factor this, you always factor it as x plus y times x minus y, just like in the last problem, when we factored x squared minus 9, we did x plus 3 times x minus 3. Okay, so I'm going to go ahead and add this as our third strategy here. Color coding here. I'm going to say, whenever you have one involving square roots when direct substitution does not work, what we're going to do is we're going to multiply by the conjugate. Okay, we're going to actually use this problem to explain why the conjugate works so well. So give us a little bit more space. I'm going to go on to the next slide here. Okay, so in this particular problem, we've already determined direct substitution doesn't work because I cannot plug in 5 into the denominator here because 5 minus 5 is 0. Okay, so what I'm going to do is I'm going to multiply the top and the bottom of this by the conjugate of the particular part of the problem that has a square root. Okay, now remember, the only thing I'm allowed to multiply by without changing something is 1. So I'm going to go ahead and multiply by the conjugate up here on the top, which is going to give me the square root of 2x minus 1 plus 3 instead of the square root of 2x minus 1 minus 3. But the thing is if I do this on top, I must do the exact same thing on the bottom. Okay, so I'm going to multiply by that same factor on the bottom, and this divided by this is 1, and let's take a look at what happens when I do this. Okay. All right, so what's happening here is I'm going to go square root of 2x minus 1 times the square root of 2x minus 1. Okay, square roots cancel each other out. That's going to leave me with 2x minus 1. Okay, now from here, what I'm going to have is plus 3 times square root of 2x minus 1. Okay, and then on the bottom, right after that, I'm going to have minus 3 times the square root of 2x minus 1. And then negative 3 times positive 3 gives me a negative 9. Okay. The reason why I'm doing this is just like foiling. This is as if I had parentheses around these, and this is the first term and the second term in this set of parentheses, and then this is the first term and the second term in this set of parentheses, okay? And what you'll notice is, just like if you were going to multiply, I don't know, x plus y times x minus y, these terms in the middle cancel out, okay? Just like multiplying any other two conjugates together, in this case, what we are left with when we're finished is the square root of 2x minus 1 squared minus 3 squared, okay? If I square the square root of 2x minus 1, the squared and the square root cancel out. I'm left with 2x minus 1. And if I square 3, I'm left with 9, and this is a subtraction because it's a difference of perfect squares, okay? Now, on the bottom, I'm not going to do any distributing here because, as you'll see in a second, there is no need for us to do that. So I'm just going to go ahead for now and leave this as x minus 5 times the square root of 2x minus 1 plus 3. And let's keep working a little bit more up on the top of this. Okay. If I combine like terms on the top, I've already gone ahead and canceled these out because I had a positive and a negative. But right here, I've got 2x minus 1 minus 9. That gives me 2x minus 10 divided by x minus 5. That's the square root of 2x minus 1 plus 3. Okay, and if I do a little bit more calculation up on the top, I've got a 2 and a 10. And notice I can remove a 2 from both of those. So I'm going to go ahead and write this as 2 times x minus 5 divided by x minus 5, which is the square root of 2x minus 1 plus 3. Okay? So, it took us a little while, but what we'll see here is by multiplying by this conjugate, what happened was I now end up with a factor that I can remove from the top and the bottom. Okay? And that factor that I'm removing from the top and the bottom is the thing that caused direct substitution to not work in the first place. I wasn't allowed to plug in 5 right here because 5 minus 5 was 0, and I can't divide by 0. Well, now that's no longer here by my use of the conjugate. And now, when I'm left with only this, we can try direct substitution again. Okay? Now when I try direct substitution, and remember, I don't need to write this anymore once I get to this step. Now I'm left with 2 times the square root of 2 times 5 is 10, minus 1 is 9, plus 3. The square root of 9 is 3, so 3 plus 3 is 6. And 2 6 simplifies down to 1/3. Okay? So the limit as x approaches 5 of this function right here ends up, when I'm done, becoming just 1/3. Okay, let's try one more like that, just because I know that can kind of be a little bit tricky for us to do this because it's a little bit new. So let's see if we can come up with one more to try it. I have one more little example, and then we will be done for this video. So let's go ahead, and for our next one, let's look at this. How about the limit as x approaches, let's try -3 of, and let's go up on the top here. Let's try let's go x plus 3, and then on the bottom let's try the square root of, we'll go let's go 10, let's go 2x plus 7 minus 1. Okay, 2x plus 7 minus 1. All right, and once again, we'll see that direct substitution does not work here. All right, it's fairly easy for us to see that because if I plug in if I plug in -3, 2 times -3 is -6, plus 7 is 1. The square root of 1 is 1, and 1 minus 1 gives me 0. Okay, so once again, direct sub is a no-go. Okay, so instead what we'll do here is, once again, we'll try to multiply by the conjugate. So for our conjugate for us here is, remember, it's going to be the exact same thing, except on the bottom here, this was a minus, we want to multiply by a plus. All right, so as we are evaluating here, we want to, I'm not going to do anything with the top. I'm just going to leave it as my 2 sets of parentheses here, because my hope is that eventually I'm going to be able to cancel out that x plus 3. But on the bottom, we'll go ahead and we'll multiply this out. Okay, so square root of 2x plus 7 times square root of 2x plus 7, I get 2x plus 7. Okay, this will give me a plus square root of 2x plus 7, and this will give me a minus square root of 2x plus 7, so those are going to cancel out. And then negative 1 times positive 1 is going to give me a minus 1. Okay. Do a little bit more work here on the bottom. 2x plus 7 minus 1. Okay, for right now, I'm just going to go ahead and call the top of that blah. 2x plus 7 minus 1 is going to give me 2x plus 6. Okay, and now I'll rewrite everything again. I can take a 2 out of the bottom there. I'm left with an x plus 3. Okay, and up on top, I'll have x plus 3. And then I'll have square root of 2x plus 7. Sorry, outside of the parentheses, plus 1. Okay, so that's x plus 3 cancels out for us. And now we can go ahead and actually just use direct substitution because I no longer have anything that's going to make me divide by 0. Now all I have left on the bottom is a 2. I don't have that x plus 3 anymore, so I can try direct sub. 2 times negative 3, as we mentioned earlier, is negative 6 plus 7 plus 1, all divided by 2. All right, this is now the square root of 1 plus 1 over 2, which gives me, square root of 1 is 1, so 2 divided by 2, which gives me an overall limit of 1. Okay, so if we're kind of looking at some different strategies to evaluate these by arithmetic or algebra, maybe, few different things we can try. We should always start by trying direct substitution. Okay, if it tells you to do it by hand, try direct substitution. Okay, if direct substitution works, I promise it'll be easy. If you're working with polynomials, in other words, things that just have nice, easy exponents, you can try factoring. We saw a couple of different problems here where factoring helped us. Originally, without factoring, we were dividing by 0, but after factoring, we were able to remove what made us divide by 0, and then we could use direct substitution. And if you happen to see something that has a square root, you can try the strategy of multiplying by the conjugate. That often helps us break up the square root, get rid of the square root, and then get rid of the factor that makes us divide by 0, thus eliminating the ability to use direct substitution initially. But once we get rid of that factor, then we can use direct substitution. Okay, so those are a few more strategies for evaluating limits that we can add on to what we were doing the other day by either graphing or looking at a table to help us evaluate. All right, one more example that I want to show you. It doesn't quite fit into exactly what we're doing today, but I'm going to go ahead and mention it anyways because it is part of it is a somewhat useful skill for us to kind of recognize here. So I'm going to go ahead and try it. So I'll say kind of a different type of example. Okay, different type of example. So let's say, for example, we had f of x equals, let's just try 3x squared minus 4. Okay, first thing that I would like us to do here is let's try to find the difference quotient. Okay, so what I'm starting to try to do here is combine some of the ideas of the difference quotient and the limit all together. So for the difference quotient for this, remember the difference quotient looks like this: f of x plus h minus f of x is from the first section of Intro to Calculus, all divided by h. Okay, so let's do some work here. If I plug in x plus h into this function, I get 3 times x plus h squared minus 4 minus f of x. Remember, I got to put this inside of parentheses. 3x squared minus 4, and then all divided by h. Okay, do some work here. If I FOILed this out, I'd get x squared plus 2xh plus h squared minus 4. I'm going to apply this negative here, which flips all the signs. So this will be minus x squared plus 4, all divided by h. Okay, and then I'm going to go ahead and distribute this 3. So this will give me 3x squared plus 6xh plus 3h squared minus 4 minus 3x squared plus 4, all divided by h. Okay, and go ahead and these 4's cancel, 3x squared and negative 3x squared cancel. And look at what we've got left on the top, 6xh and a 3h squared. Notice that both of these have an h. So I can take that h out, and I'm left with 6x plus 3h all divided by h. Okay. And then I can take out those h's, and what I'm left with is 6x plus 3h. Okay. So one of the reasons why I'm asking you to find that difference quotient first is because a follow-up question to this might be for me to ask you, okay, what's the limit as h approaches 0 of f of x plus h minus f of x divided by h? Okay. Well, notice right here that if you try direct substitution at first, we would end up dividing by 0, but we don't want to divide by 0. Okay. So what we ended up having to do right here was we had to use our function, plug in x plus h for x, and then go ahead and use this difference quotient. There's no need for me to do all of this work again because I already know that when I do this difference quotient, I get 6x plus 3h, but what is this asking me for? What's the limit as h approaches 0? I can now just go ahead and use direct substitution with my difference quotient. 3 times 0 gives me a difference quotient of, a limit of 6x, okay? Which is nice because that's what I wanted in the first place. Was I wanted to figure out what was the limit as h approaches 0. Now, a further extension of that would be for me to ask you this. What's the limit as h approaches 0 of f of, let's say for example, 5 plus h minus f of 5 divided by h, okay? And this is sort of a form of us doing substitution here, which is why I try to include it in this section, even though it doesn't completely fit into what we've talked about before, because notice what's happened here is instead of an x, they've substituted in a 5, okay? But this, other than that, this is the exact same problem as what you see here. Okay, I said what find the limit as h approaches 0 of this difference quotient. This says find the limit as h approaches 0 of a difference quotient, but instead of having x, we've substituted in a 5. Okay. Well, think about it. On the last problem, on part B here, when this was an x instead of an an x instead of a 5, when we evaluated this, we got 6x. Well, this time, the only thing that's happened is instead of having an x, we've substituted in a 5. Well, along the same lines of thinking, what we can now do is take this answer that we got on the last problem, and instead of having 6x, in place of that x, we can plug in a 5. And when I'm done here, 6 times 5 gives me a final answer of 30. Okay? So by starting with the difference quotient, calculating that difference quotient, finding the limit of that difference quotient as we approach an h value of 0, and then taking this difference quotient and substituting something in for x, we were able to evaluate this limit right here by taking our answer from part B and plugging in 5 for x, okay? So it's a little bit like a form of substitution. I'm not going to put it on our list because it doesn't follow the same type of strategies of factoring and using a conjugate, but you might see me set up a problem this way and have you start by finding a difference quotient and then calculating a couple of limits with that difference quotient as you have seen us do right here in this problem. Okay. All right, guys, that's all I've got for this one. I'll put an assignment up here in just a little bit, and I hope you guys have a good rest of your day, and I will talk to y'all again next time we have a Zoom meeting.